Hi, welcome back. In this lesson, you will learn about informed search, a search strategy that uses problem-specific knowledge beyond the definition of the problem itself. I will show you these strategies, these algorithms, the best first search, greedy best first search, A-star search, and I will also talk about heuristics. In the previous lesson, you learned about uninformed search, also known as blind search. BFS, DFS, and UCS are the blind search strategies we looked into. These search strategies do not have any concept of right direction. They can only recognize goal once it is achieved. They can only determine whether a state is a goal or not. Now, you will learn about informed search, also called heuristic search. Heuristic search have a rough idea of how good various states are and use this knowledge to guide our search. Best first search is the general approach we consider for heuristic search. A node is selected for expansion based on an evaluation function, f of n, wherein f of n is an estimate of the desirability of a node. The implementation of best first search is identical to that for uniform cost search, except for the use of f instead of g to order the priority queue. The fringe of best first is a queue sorted by decreasing order of desirability. Thus, the first element in the fringe that will be expanded is the most desirable node in the fringe based on f. And the choice of f determines the search strategy. We will look at two popular informed search strategies, the greedy search and the A-star search. Most best first algorithms include as a component of f a heuristic function denoted as h of n. H of n is the estimated cost of the cheapest path from the state at node n to a goal state. This adds domain-specific information to select the best path. The greedy best first search or greedy search uses h of n as its evaluation function. Greedy search expands the nodes that appears to be closest to goal. Take note of the word appears. It means, it seems, it looks, it is somehow a good guess. So in Filipino, maybe we can call that a hula. So let's go back to this route finding problem in Romania from Arad to Bucharest. And then the step cost that's indicated here are values in kilometers. So you've seen this map in the previous lesson when we discussed about uninformed search or blind search. So we traverse the path using some blind search algorithms like BFS, DFS, and UCS. Now we're going to find the solution to this problem using informed search strategies. And here, the first strategy that we're going to use is the greedy search. So I mentioned earlier that the greedy search uses as its evaluation function an h of n, or a heuristic function. And for this problem, what is a possible heuristic for this problem? So here, heuristic is the cheapest path from any state n to a goal state. And that can be estimated by the straight line distance of a city, or of a city, or from a city to Bucharest, which let's say here on on the table at the right part of the slide. So the straight line distance, for example, here we have Arad. It means that from Arad to Bucharest, if we draw a straight line between them, that distance is 366 kilometers. From Craiova to Bucharest, where is it? There. That distance is 160. So this is an example of an h of n, or a heuristic. So using this straight line distance to Bucharest as our h of n, let's traverse, or let's try to look for the solution following the greedy best first search. So our initial state is Arad, and then you will notice that here f of n, or the evaluation function, is just, since it's just equal to h of n, so it's 366. But since it's the initial state, it's the root of our tree. So we look at from Arad, what are our options? Timisoara, Sibiu, and Zerin. So here you will notice Sibiu, it has the lowest SLD, or short line distance, to Bucharest. That's why we will choose Sibiu there. And then from Sibiu, let's look at Sibiu. What are our options? What are the options? We have Făgăraș, Micu, Vlcea, Arad, and Ardea. Let's take a look at our SLD table. So the shortest is Făgăraș. Therefore, we're going to choose Făgăraș there, and Făgăraș will be expanded. So here are our fringe there. And then from Făgăraș, we have two options, Sibiu and Bucharest. Of course, this is our goal state, so we go there. So we have here the path, the cost of the path, which is 140 plus 99 plus 211 is 450. So that's the cost of the path from Arad via Sibiu, Făgăraș, and there to Bucharest. So it's this one. We computed that Arad 140, Arad to Sibiu 140, Sibiu to Făgăraș 190, and here 211. Okay. So that's our solution, or the path that we found using the greedy search approach. So is greedy search optimal? Is it complete? Let's try to look at some example to know if it's optimal. So the value we got, or the total cost that path cost that we got from using greedy search is 450. However, there is an alternate path, which is Arad, Sibiu, Rymnicu, Pitești, and Bucharest, which has a total of 418. So this one is definitely lower than the 450 that we got, the solution we got earlier using greedy search. Therefore, greedy search is not optimal. And the time complexity and space complexity of greedy search is OB to the M for both time and space complexity. Is it complete? Let's take a look at this. So greedy search sometimes causes unnecessary nodes to be expanded. For example, if we start with IASI and our goal node or state is Figueras, let's take a look at the map again. So this is the initial state here, IASI, and we want to go to Figueras. There, let's put a star there. So you'll notice that NIAMP is closer to Figueras and probably has a lower SLD or straight line distance to Figueras than Vaslui, than this one. Okay, so this will be expanded, the NIAMP, this node. And however, this is a dead end. There is no path from NIAMP to Figueras. Therefore, since this has no other branches or path, this will expand IASI. However, since our basis for f of n, or our evaluation function, is the heuristic value or heuristic function, again, NIAMP has a shorter straight line distance to Figueras. Therefore, it will expand that node, and then we'll do it again and there. Therefore, with that problem, greedy search will not be able to find this path, which is the solution to the problem. Therefore, greedy search may not be complete. So it may not find, so it's not complete, it may not find the solution because it can get stuck in loops or in an infinite loop. Therefore, our goal is not to minimize the distance from the current head of our path to the goal, but to minimize the overall length of the path to the goal. We learned previously that g of n gives the path cost from the start node to node n, and h of n is the estimated cost of the cheapest path from n to the goal. Thus, if we are trying to find the cheapest solution, a reasonable thing to try first is the node with the lowest sum of g of n and h of n. This is the estimated cost of the cheapest solution through n. So that's here. H of n equals g of n plus h of n. Provided that the heuristic function h of n satisfies certain conditions, such as admissibility and consistency, this search strategy is both complete and optimal. An admissible heuristic is one that never overestimates the cost to reach the goal. So if the true cost of the optimal path from n to a goal node is h star of n, h of n is admissible if h of n is positive and h of n is less than or equal to h star of n. So this one is the condition for admissibility. An admissible heuristic is always optimistic and never overestimates the true cost of a solution along the current path through n. A heuristic h of n is consistent if for every node n and every successor n prime of n generated by any action A, the estimated cost of reaching the goal from n is less than or equal to the step cost of getting to n prime plus the estimated cost of reaching the goal from n prime. So a shorter version of that is here. So if h of n is less than or equal to, this one is the step cost from n to n prime. And plus h of n prime, or the heuristic function from n prime to the goal state. This is a form of the general triangle inequality, which states that each side of a triangle cannot be longer than the sum of the other two sides. So, like shown in here. It is also important to note that every consistent heuristic is also admissible. So for example, here, I'm going to show you how this one, the proof of this one, if h is consistent, let's say h is consistent, we have h prime with this equation, h prime of n is equal to g of n prime plus h of n prime. So we're going to substitute g of n prime with this value, since g of n prime is actually g of n, the cost to n, plus the step cost from n to n prime. And then take a look at this one. Here, this part is the same with this. Substituting this value to that one, we have here h of n, and we use this symbol. Therefore, in the end, we have h of n prime is greater than, f of n prime is greater than or equal to f of n, which means that, so this means that f of n is non-decreasing along any path, meaning it is admissible. If the evaluation function f of n equals g of n plus h of n, where g of n is the cost of the best path to n, and h of n is an admissible heuristic, then the best first search with this evaluation function is called A-star search. A-star search is an important AI algorithm developed by Fikes and Nilsson in early 70s. It was originally used in the Shaky robot and which is the first mobile robot with the ability to perceive and reason about its surroundings. So let's go back to our ARED to Bucharest problem again. So now we are going to follow or to use the A-star search algorithm, wherein f of n, or the evaluation function, is g of n plus h of n. So here you'll see that the initial state is ARED, and of course g of n is 0 plus the h of n, which is 366. Next, expanding that node, we have on the fringe here three candidates on the fringe. We have Sibiu with g of n of 140 plus the h of n is 253. Where is Sibiu? There. Equals 393. Timizora has f of n, which is equal to 447, and Zerin 449. We choose the lowest, it's 393, which is Sibiu. And then Sibiu, we expand Sibiu. We have now ARED, Fagaras, Oradea, Rimniku, Visaya, Timisoara, Zerin. And then let's take a look at the evaluation function, the value for f of n. For ARED is 646, Fagaras it's 415, 671, and so on. So the lowest is Rimniku, Visaya. So that's the node that we're going to expand. And then let's take a look at the nodes under Rimniku, Visaya. There is 526, 417, and 553, and then 647 for ARED. Fagaras is 415, Oradea, Zerin, Timisoara. So among the nodes in the fringe, we choose this one, Fagaras, the lowest. Therefore, Fagaras is expanded, and then we'll notice Fagaras is the lowest, and then we'll notice that we have the values here, 46, the fringe are ARED, Sibiu, Bucharest, and the lowest is Pitesti. Therefore, we choose Pitesti there. And then there is Bucharest. So now we found this path, ARED, Sibiu, Rimniku, Visaya, Pitesti, and then Bucharest, which is actually the path that has the lowest total cost of 418. Therefore, Here are the properties of the A-star search. We can say that A-star search is complete unless there are infinitely many nodes with f less than or equal to f of g. The time is exponential, and the space keeps all nodes in memory. So it is kind of expensive also. It is optimal. Yes, we found the shortest path from Arad to Bucharest, provided that the heuristic is admissible. And if it's a graph search, it is consistent. So to solve that complexity problem, the simplest way to reduce memory requirements for A-star is to adapt the idea of iterative deepening to the heuristic search context, resulting in the iterative deepening A-star algorithm, or IDA asterisk, or IDA star. The main difference between IDA star and standard iterative deepening is that the cutoff used is the f cost g plus h rather than the depth. At each iteration, the cutoff value is the smallest f cost of any node that exceeded the cutoff on the previous iteration. IDA star is practical for many problems with unit step costs and avoids the substantial overhead associated with keeping a sorted queue of nodes. So heuristics are intended to orient the search along promising paths. So we have to remember that heuristics should serve as our guide. And the time spent computing the heuristics must be recovered by a better search. Also, the heuristics, the computational time needed for the heuristic function should not be very high that you won't be able to perform or to execute the search in a reasonable time and memory allocation. So yeah, choosing the right heuristic is very important. It should not be very simple, and it should not be too complex as well. So if you want to learn more about informed search, it's part of chapter 3 of the Russell and Norvig book on artificial intelligence. Thank you for listening and have a great day.